Hey, welcome. Today, we're going to talk about three words you use all the time: work, energy, and power. But here's the thing: I'm willing to bet you're not using them quite right, at least not in the way a physicist would. Let's find out why.
So let me ask you something. Right now, sitting there watching this, are you working? I mean, you're concentrating, you're using your brain? Most of us would say, yeah, of course. But in the wild world of physics, the answer is probably no.
Think about someone cramming for an exam. They're spending hours reading, thinking, solving problems. They are definitely working hard in the normal sense of the phrase, right? I mean, they're going to be exhausted. But from a scientific point of view, they're doing almost zero actual work.
Or what about this? You're pushing against a giant boulder with every ounce of your strength. Your muscles are burning, you're sweating, you're completely wiped out afterwards. But if that rock doesn't move one single inch, you've done absolutely no work on it. How is that even possible? Okay, so this is where we really need to separate our everyday language from the super precise language of physics. Let's get clear on what work actually is. You see, in our daily lives, work can be anything from doing homework to just thinking really hard. But in science, the definition is way stricter. Work is only done when a force makes something move. So pushing a shopping cart, that's work. Lifting a book off a table? Yep, work. But just standing there holding a heavy box? Not work. Isn't that weird? So here's the deal. It's actually pretty simple. For work to happen in the physics world, two things must be true. Number one, a force has to be applied to something. And number two, this is the big one, that something has to actually move. It has to be displaced. If one of those is missing, no work is done, period. And this gives us this beautifully simple formula. Work equals the force you use multiplied by the distance the object moves or its displacement. So think back to that rock. You're applying a whole lot of force, but the displacement is zero. Anything times zero is zero. So zero work. And when you're studying, there's no force moving an object. Again, zero work. This little formula is everything. And we have a special unit to measure work. It's called the joule. So what on earth is 1 joule? Well, imagine picking up a small apple. The force you need to do that is about 1 Newton. Now lift that apple 1 meter straight up. The amount of work you just did is 1 joule. Okay, so this brings up a pretty logical question, right? If work is all about using force to move things, well, what do you need to have in order to do that? What's the secret ingredient? And the answer, of course, is energy. You can literally think of energy as the currency for doing work. If you don't have any energy, you can't buy any work. Nothing happens. So the official scientific definition of energy is just that, the capacity to do work. And hey, look at the unit. It's the joule, the exact same as work. That is not a coincidence. It's the universe's way of showing us how deeply connected they are. Energy is the potential to do work, and work is what happens when you use that energy. Now, energy comes in all sorts of flavors. You've got heat, you've got the chemical energy in your food, electrical energy powering your screen right now, light energy, the list goes on. But for what we're talking about today, we're going to zoom in on the two big types of what's called mechanical energy. And these two superstars are kinetic energy, that's the energy of motion, and potential energy, which is basically stored energy. Kinetic energy is pretty easy to get your head around. It's the energy something has because it's moving. A car speeding down the highway, a coconut falling from a tree, that's kinetic energy in action. Potential energy is the energy of waiting. It's the energy that's stored up in a stretched rubber band or in a hammer you've lifted up right before you swing it down. It's potential, just waiting to be turned into something else. So the formula for kinetic energy is half of an object's mass times its velocity squared. Now, that little squared symbol on the V is a really big deal. It means that an object's speed has a massive effect on its energy. If you double your speed in a car, you don't just double your kinetic energy, you actually get 4 times as much. And for the potential energy you get from gravity, the formula is also super neat. It's the object's mass times the force of gravity times its height. So the higher you lift something up, the more work you have to do against gravity, and the more potential energy you're packing into it. All right, this brings us to one of the most fundamental, most important laws in all of science. Seriously, this is a big one. It's like energy's golden rule. And here it is, the law of conservation of energy. You cannot make energy out of thin air, and you can't make it disappear. The total amount of energy in the universe is constant. All it does is change its costume.
It might go from chemical to heat or potential to kinetic, but the total amount never ever changes.
A falling object is the perfect example. Picture holding a ball way up high. At the very top, before you let go, it's not moving, so it has zero kinetic energy. It's all potential energy because of its height. Then you drop it. As it falls, the height gets lower, so its potential energy goes down. But that energy doesn't vanish. It transforms into kinetic energy, making the ball go faster and faster. And right before it hits the ground, it's at its absolute fastest, max kinetic energy, and has basically zero potential energy left. The total energy stays the same the whole way down.
So we've got work, which is force times distance. We've got energy, which is the ability to do that work. But there's one more piece to this puzzle we need to talk about, the element of time. And that, my friends, is where power comes in.
Power isn't about how much work you do. It's about how fast you do it. It's the rate at which you use energy. The formula couldn't be simpler. Power is just the work you do divided by the time it takes, and we measure it in watts. So 1 watt just means you're doing 1 joule of work every single second.
This example makes it crystal clear. Okay, look at girl A and girl B. They have the same weight, and they both climb a rope to the same height, 8 meters. So if you look at the work done row, it's identical. They both did exactly 3,200 joules of work. But, and this is the key, girl A scrambled up that rope in just 20 seconds, while girl B took 50 seconds. So when we calculate the power, girl A is way more powerful, 160 watts compared to just 64 for girl B. Same work, totally different power.
Okay, so let's wrap this all up. If you remember nothing else, remember these 4 key things. First, work requires both a force and movement. Second, energy is the capacity you need to do that work. Third, energy is never created or destroyed, it just changes form. And finally, power is the stopwatch on work. It tells you how fast you're getting it done.
And I'll leave you with a final thought to chew on, bringing us right back to that rock at the beginning. If you push on it and it doesn't move, you do zero work on the rock. But you still get tired. You've obviously burned a bunch of energy. So where did that energy go? Something to think about. Thanks for tuning in.